For most of the 20th century, our mental map of the solar system was remarkably tidy. We viewed our neighborhood as a collection of 9 isolated spheres, each tracing a lonely path through an otherwise empty void. The discovery of Pluto in 1930 cemented this paradigm. When Clyde Tombaugh identified that distant speck of light, he provided the final anchor for the 9-planet model that would define science education for generations. That model began to fracture in the early 2000s. As telescope technology advanced, astronomers began peering into the Kuiper Belt, a massive debris field beyond the orbit of Neptune, and found that the outer reaches were far more crowded than previously thought. The turning point arrived in 2005 with the discovery of Eris. This icy object, drifting billions of miles away, possessed more mass than Pluto itself. This find triggered an immediate scientific crisis. If Pluto was a planet based on size and distance, then Eris required the same title, along with dozens of other massive objects likely waiting to be found in the deep freeze of the outer solar system. The discovery of Eris forced a rigorous re-evaluation of the physical and dynamical properties required for an object to be considered a world. In 2006, the International Astronomical Union gathered to ensure that planet was consistently defined. Their resolution created an entirely new category to account for these massive, icy discoveries. They introduced the term dwarf planet, a designation based on 3 specific physical criteria. First, the object must orbit the Sun directly. This rule excludes moons and satellites, ensuring it is an independent member of the solar system. Second, the body must reach hydrostatic equilibrium. This occurs when mass and gravity overcome material rigidity, crushing it into a spherical shape. Icy bodies can round out at 400 kilometers wide, while rocky bodies require nearly 900 kilometers. The final rule is the clearing of the neighborhood. While a true planet has the gravitational power to sweep its orbit clean, a dwarf planet shares its orbital path with thousands of other pieces of debris. A dwarf planet effectively combines the internal geology of a true planet with the cluttered, shared orbital dynamics of an asteroid. Currently, only 5 objects in our solar system have been officially confirmed to meet these requirements. Ceres is the closest, located in the asteroid belt between Mars and Jupiter. It is a geologically distinct world, featuring highly reflective salt deposits that glow from the floors of its impact craters. In the outer system, we find Haumea and Makemake. Haumea spins so rapidly that its physical shape has been stretched into a flattened, elongated football, while Makemake is covered in methane ice, so pure it makes the world exceptionally bright. Eris remains the most massive member of the group, drifting in a distant, tilted orbit that defines the known edge of the roster. Then there is Pluto, which was reclassified from the 9th planet to the most famous prototype for this new class of objects. High-resolution data from the New Horizons mission proves these worlds are geologically active. On Pluto, we see evidence of internal heating, jagged mountains of water ice, and complex atmospheric hazes. These discoveries shifted the focus of astrophysics away from simple planet counting and toward the study of a diverse spectrum of evolving worlds. The 2006 IAU decision aligned our definitions with a more complex reality. We now recognize the solar system featuring massive, cluttered disks of ancient material extending billions of miles into space. The current roster of 5 is just the beginning of our exploration. Objects like Gonggong, Quaoar, Sedna, and Orcus are already on a massive waiting list, with astronomers estimating that hundreds more are waiting to be officially identified. Modern instruments like the James Webb Space Telescope are currently detecting thermal signatures and complex organic molecules on these distant surfaces. These bodies preserve the primordial materials of our solar system in a pristine deep freeze. They populate the farthest reaches of our neighborhood, establishing a dense and chemically active frontier that stretches far beyond the classical planets.
The main asteroid belt is frequently viewed as a cosmic junkyard, a ring of dry, cratered rocks drifting between Mars and Jupiter. At the center of this region sits Ceres. At 590 miles wide, it contains a full third of the mass and the entire belt. For over 2 centuries, astronomers looked at Ceres and saw only a larger version of its neighbors, a barren, gray stone drifting in the dark. That model held until 2015, when NASA's Dawn spacecraft arrived to map this unexplored behemoth for the first time. As the probe approached, its cameras captured a cluster of bright, glowing points that indicated internal activity researchers didn't think was possible in this part of the solar system. Deep inside the 57-mile-wide Okator crater, Dawn found spots of blindingly bright material glowing against a surface as dark as asphalt. The discovery triggered a wave of speculation over whether these were exposed sheets of water ice or perhaps active geysers venting into space. To identify these spots, planetary scientists had to discard the idea of Ceres as a solid chunk of rock and model its internal chemical history. These surface markings became the starting point for a forensic investigation into the asteroid's hidden interior. Dawn spectrometers eventually identified the bright material as a massive deposit of sodium carbonate salt, not water ice. Salt deposits of this scale imply the evaporation of liquid, which raised a new question: how a supposedly dead rock could produce enough liquid to flood the floor of a crater. This diagram shows that Ceres is organized into distinct internal layers, a process known as differentiation. Analysis of the mantle reveals it is up to 25% water by mass. By volume, it contains more fresh water than all of Earth's lakes and rivers combined. The presence of this much water forces a total reclassification of Ceres from a dry asteroid to a dynamic, wet world. The engine driving these surface changes is cryovolcanism, a process where ice and brine erupt instead of molten rock. Deep reservoirs of liquid, muddy brine sit pressurized beneath the rigid outer crust. When an asteroid strikes the surface, the impact cracks the crust, giving that pressurized brine a sudden escape route to the surface. In some regions, internal pressure builds independently, pushing the crust upward to form massive 3-mile-high ice volcanoes like Ahuna Mons. When this brine reaches the vacuum of space, the water instantly flashes into vapor, leaving only the white sodium carbonate salt behind. The famous bright spots are the forensic scars of these eruptions, marking where a hidden, watery underworld recently breached the surface. Along with the salt, Dawn detected ammonia-rich clays and complex organic molecules scattered across the surface. Ammonia and these specific organics only condense at the freezing temperatures found in the outer solar system, far beyond Ceres' current orbit. This suggests that Ceres likely formed past Jupiter and migrated inward to the asteroid belt over billions of years. Ceres is an ancient intruder, carrying the chemical signatures of the outer solar system into the inner rocky belt. The Dawn mission's findings reveal that Ceres is a relic ocean world, an ancient body whose evolution was dominated by water. Billions of years ago, it likely possessed a warm, muddy subsurface ocean that spanned the entire globe before freezing from the top down. Identifying an environment that could support life requires locating 3 specific ingredients. This diagram overlays those requirements. According to the mission data, Ceres contains the liquid water, the organic chemistry, and the chemical energy necessary to support microbial organisms. While life is not currently thriving on the frozen surface, ancient Ceres possessed the exact recipe required for life to emerge. The search for habitable environments often looks toward the distant moons of the gas giants, but the blueprints for a habitable ocean world are sitting right next door in our own asteroid belt. At 40 Kelvin, 400 degrees below 0 Fahrenheit, and orbiting billions of miles from the Sun on a 248-year track, Pluto resides in a deep freeze. For decades, the working model for the outer solar system was straightforward. Any object this small and distant was expected to be a geologically dead, heavily cratered ball of ice. In July 2015, NASA's New Horizons probe flew past and provided the first high-resolution data of the surface. Instead of an ancient, battered rock, the probe sent back images of towering mountains and massive plains entirely free of impact craters. The surface was geologically young and currently reshaping itself. Identifying the source of this energy requires a descent through the Pluto system, layer by layer. Approaching Pluto, the first encounter is with its massive companion moon, Charon. This animation shows how the two bodies interact. They form a binary system, meaning they orbit a shared center of mass, a point in empty space right between them. This setup creates a shifting gravitational field. Caught in the middle of it are Pluto's 4 smaller outer moons, Nix, Hydra,
Kerberos, and Styx. This academic paper documents the effect. Because of the erratic gravity, these small chunks of ice do not keep one face locked toward their planet. Instead, they tumble chaotically. This orbital instability reflects the unconventional nature of the entire system. Moving closer to the surface, you hit the atmosphere. Despite its low gravity, Pluto holds on to a thin layer of nitrogen gas that extends hundreds of kilometers into space. This photograph from the New Horizons probe captures the distinct blue haze layers suspended in that upper atmosphere. Up there, solar radiation interacts with trace amounts of methane gas, breaking it apart and reforming it into complex, heavy hydrocarbons. Eventually, those heavy molecules precipitate out of the sky as organic rain, coating Pluto's surface in a reddish-brown substance known as tholin. Pluto's sky functions as a massive chemical engine, continuously altering the planet's surface composition. This map highlights Sputnik Planitia, a Texas-sized basin at 40 Kelvin. Panning to the borders around the Wright and Tartarus regions, water freezes so rigidly it acts like solid bedrock, forming mountains as tall as the Rockies. Nitrogen, conversely, takes on the consistency of soft toothpaste, spreading out into vast, creeping glacial plains. Incredibly, these towering water ice mountains are actually detached icebergs, slowly drifting within a sea of flowing nitrogen ice. Nearby, massive ice volcanoes have recently erupted, but instead of spewing molten rock, they unleash flows of icy, ammonia-rich slush. A surface crust that shifts and erupts requires an active heat source hidden below ground. To find that heat, we have to dive beneath the ice. Beneath the crust sits a global ocean of liquid water, potentially up to 200 kilometers deep. This cross-section reveals Pluto's heat engine. The rocky core emits radiogenic heat upward into a vast liquid ocean. Ammonia mixes in, acting as a potent antifreeze. Finally, a layer of trapped methane gas hydrates caps the ocean, insulating and trapping the thermal energy inside. This three-part system, radiogenic heat, a potent chemical antifreeze, and strong physical insulation, is the heartbeat powering Pluto's geological activity. Pluto's active systems require a significant update to our understanding of the outer solar system. We now know that extreme cold and a vast distance from a host star do not result in a dead, inactive world. Internal radioactive decay and deep subsurface chemistry are sufficient to sustain planetary activity, independent of sunlight. The discovery of liquid water and persistent heat on a body this small changes our expectations for the Kuiper Belt and beyond. It suggests that active environments might exist in the darkest corners of the universe, sustained by internal physics rather than starlight. Out at the extreme edge of our solar system lies a region of icy debris called the scattered disk, and drifting through the dark, nearly 97 astronomical units away from the Sun, is the dwarf planet Eris. At this distance, almost 10 billion kilometers away, the Sun is little more than an unusually bright star in an otherwise black sky. Eris exists in a state of deep, permanent isolation, where temperatures hover just a few degrees above absolute zero. You might expect a world out here to be a dark, irregular lump of ice and rock, yet Eris presents a physical paradox. It is nearly perfectly spherical, and it is shockingly bright. Eris has an albedo of 0.96. That means it reflects 96% of all the sunlight that hits it. While a typical rocky asteroid absorbs most light, Eris bounces almost all of it right back into space. To anyone looking through a telescope, Eris appears to be a static, pristine world, perfectly preserved in the freezing dark. But Eris is not standing still. It follows a highly elliptical, 557-year loop around the Sun. Over the centuries, its distance from the inner solar system drastically shifts, and right now it is near aphelion, the absolute furthest edge of its orbit. When Eris reaches this outer boundary, the surface temperature drops so low that the dwarf planet's entire atmosphere physically freezes. The airborne gases collapse. They fall to the desolate surface as pristine methane and nitrogen snow, burying the world in a fresh layer of ice. That blinding white surface is an illusion of stillness. The bright shell we see today is actually the frozen result of a collapsed atmosphere. To understand what lies beneath that ice, we must look at Eris's tiny, dark moon, Dysnomia. It takes Dysnomia exactly 15.7 days to complete one orbit around the dwarf planet. In astrophysics, a moon is a measuring tool. By observing exactly how long a moon takes to orbit, astronomers can use orbital mechanics to calculate the mass of the parent planet pulling on it. When they ran those numbers for Eris, the results were staggering. In total volume, Eris is actually slightly smaller than Pluto, but on a scale, Eris is 27% more massive. Packing that much mass into a smaller space gives Eris a density of around 2.5 grams per cubic centimeter. That number dictates that Eris is composed of roughly 85% solid rock. This density refutes the idea of Eris as a simple ball of ice. Instead, it reveals a heavy, rocky world hidden beneath the surface. Which raises a historical question. How did an object forming in the deep, icy outer solar system become so heavily dominated by solid rock? The leading theory points to a catastrophic event billions of years ago, a violent kinetic impact between two massive planetary bodies. The force of this ancient collision blasted away the majority of Eris's lighter, primordial outer ice mantle, ejecting it into space. That ejected icy debris eventually coalesced in orbit to form the dark moon Dysnomia, leaving only the heavy, dense rocky core of the original planet behind. Eris is a scarred survivor of a violent past, and that massive rocky core sets the stage for the activity happening inside it today. If we move deep beneath that frozen crust, down into Eris's massive rocky core, we find a high concentration of heavy radioactive elements. Over billions of years, the steady decay of these radioactive elements acts as a geothermal engine. This steady process generates significant internal heat. But how does all that trapped heat escape? Unlike the rigid shells of other distant bodies, the heat inside Eris creates a convecting ice shell. Planetary scientists call this a soft cheese model. Solid ice warms from below, churning and circulating in convection currents. This internal churning connects directly to the exterior, actively smoothing surface topography to keep Eris remarkably spherical. We now have chemical proof of this internal engine, thanks to recent spectroscopic observations made by the James Webb Space Telescope. This chart compares the chemical signatures of ice in our solar system. It shows the high deuterium levels normally found in primordial ice, set against the unusually low deuterium to hydrogen ratios that JWST discovered in the methane on Eris's surface. That chemical signature marks the methane on Eris as something other than primordial ice. This material has arrived on the surface much more recently than the planet's original formation. Instead, it points to an ongoing source. This fresh methane is likely a thermogenic gas, continuously bubbling up from hydrothermal processes within Eris's warm core. Eris possesses a warm, churning interior, a dynamic world that continues to chemically evolve at the frozen edge of our solar system. The Kuiper Belt is the solar system's deep freeze. Lying billions of miles beyond Neptune, it operates as a dark, quiet graveyard, filled with ancient, spherical worlds drifting peacefully in the cold. But one object out here breaks every established rule of this silent frontier. It is a dwarf planet named Haumea. To understand why this world is so distinct, you have to look at how it spins. While Earth takes a leisurely 24 hours to complete a single day, Haumea completes a full rotation in just under 4 hours. It is the fastest spinning large object in the known solar system. That extreme rotational velocity has severe physical consequences. The centrifugal force is so intense that it pushes the equator outward and flattens the poles, stretching the entire planet into a shape that looks remarkably like a squashed football. Then there is the matter of its mass. Objects in this region of space are typically huge balls of ice. Haumea, however, is incredibly dense, possessing a massive, solid, rocky core hidden beneath a thin outer glaze of frost. Fast, stretched to the breaking point, and unnaturally dense. These physical contradictions point toward a singular, catastrophic disruption. By analyzing the planet's modern state, we can work backward to the moment it was broken. Evidence of that event surrounds the planet. In 2017, astronomers watched Haumea pass in front of a distant star and noticed a sudden dip in the starlight. That shadow revealed a 70-kilometer-wide ring of debris circling the planet's equator, making Haumea the only object beyond Neptune ever discovered with a ring system. A little further out, the dwarf planet is flanked by two moons, Namaka and Hiaka, which are locked in erratic, dynamically excited orbits. And trailing behind Haumea, scattered along its exact orbital path around the Sun, is a massive swarm of icy fragments known as a collisional family. A localized ring, two chaotic moons, and a wake of shattered ice indicate that Haumea is the epicenter of a massive ancient fragmentation event. Roughly 4.5 billion years ago, the early solar system was a chaotic, crowded shooting gallery. During this period of intense bombardment, another large planetary body slammed into a primordial, spherical Haumea at incredible speed. The impact hit at a sharp angle, a glancing blow that acted like a massive cosmic billiard shot, transferring an enormous amount of angular momentum into the surviving body and instantly kicking off its frantic 4-hour spin. Because a planet is massive enough that its own gravity acts like a fluid, a principle called hydrostatic equilibrium, that sudden, extreme rotational energy forced the molten rock to settle into the stretched, football-like shape we see today. This exact same strike explains the density. The kinetic force of the impact was so great that it shattered Haumea's thick, primordial outer ice shell, violently ejecting millions of tons of frozen water into deep space and leaving only the dense, rocky core behind. A single kinetic event dictates the fundamental physics of this world, tying the anomalies of spin, shape, and composition together. But all that ejected ice didn't just vanish. The physics of the crash dictated exactly where the shrapnel ended up. Every planet has a gravitational boundary called the Roche limit, where tidal forces are stronger than the gravity pulling loose debris together. The ice fragments inside this boundary hit an invisible wall. Unable to clump, they flattened into Haumea's 70-kilometer-wide orbital ring. Just outside that boundary, the rules change. Escaping ice chunks were free to merge, eventually coalescing into the two moons, Hiaka and Namaka. And the icy fragments that were blasted away with the highest velocity managed to escape Haumea's gravity entirely. They scattered deep into the outer solar system, forming the trailing wake of the collisional family we observe today. First, the localized ring, then the chaotic moons, and the sprawling icy wake are the literal frozen shrapnel of an ancient hit-and-run. This collision hypothesis serves as the grand unifying theory for the entire system, yet modern observations of Haumea reveal one final paradox. The thin layer of ice that managed to stay on the surface is as bright as fresh snow, and it is made almost entirely of highly ordered crystalline water ice. Out in the Kuiper Belt, temperatures hover near absolute zero. Over millions of years, constant bombardment from cosmic rays and solar radiation should break down that highly ordered crystalline lattice, degrading it into a disorganized state known as amorphous ice. The fact that we still see an intact crystalline structure today indicates that something inside the planet is generating fresh energy right now, counteracting the radiation and keeping the molecular structure perfectly organized. Haumea is not a dead, frozen relic. It is an active, dynamic system continuously refreshing its own surface. The energy powering this resurfacing process likely comes from two internal engines: heat generated by the radioactive decay of elements deep within its rocky core, or intense tidal friction pulled from the erratic orbits of its two moons. These observations show that the Kuiper Belt contains active geological frontiers, where violent interactions and internal heat break the primordial deep freeze. Out in the dark, spinning wildly on its axis, Haumea stands as a living monument to the chaotic forces that built and broke the outer edges of our celestial neighborhood. Billions of miles away from Earth, deep within the dark, icy debris of the Kuiper Belt, sits a frozen, isolated, and highly mysterious world. Spotted near the Easter holiday in 2005, astronomers originally nicknamed this icy body Easter Bunny. It eventually received a more official name, Makemake, after the creator god in the mythology of the Rapa Nui people of Easter Island. Makemake is substantial. It measures roughly 2/3 the size of Pluto. Out in this distant orbit, it endures a punishing surface temperature of -243 degrees Celsius. Because it shares that massive scale and extreme cold with Pluto, astronomers assumed it behaved similarly. They expected Makemake to harbor a thick, global atmosphere composed of nitrogen and methane. Projecting the traits of one world onto another creates a massive blind spot. When scientists finally got a chance to test that assumption, the results defied the existing models. In 2011, a global campaign aimed some of Earth's most powerful ground-based observatories, including the massive Very Large Telescope in Chile, directly at Makemake. They were waiting for a stellar occultation, when a planet passes in front of a distant star. If an atmosphere is present, the starlight fades out gradually. But when Makemake made its pass, the light instantly dropped to zero. There was no slow fade. This sharp cutoff in starlight points to a stark conclusion. Makemake lacked a global atmosphere. To the observers on Earth, it appeared to be a dead, airless rock. A completely naked surface contradicts the physical expectations for a body of its class. An object this size, floating in the Kuiper Belt, should have a gas envelope. To figure out exactly where the missing atmosphere went, investigators had to look directly at the frozen ground. Spectroscopic data, measurements of how light interacts with the planet, shows that Makemake is highly reflective. Its surface is paved with massive sheets of frozen methane. Mixed into that ice are tholins. These complex organic compounds are created when solar radiation bakes simple hydrocarbons, giving the planet its distinct reddish-brown stain. This raw chemical inventory deepens the mystery. If the primary ingredient for an atmosphere, methane, is sitting right there on the surface in massive quantities, why isn't it evaporating to form a global gas layer? Having the chemical ingredients for an atmosphere is only half the equation. A planet also needs the mechanical ability to hold on to those gases, directing researchers to look at a completely different variable: gravity. For over a decade, astronomers struggled to calculate Makemake's surface gravity. The standard way to measure a distant planet's mass is to track how its gravity pulls on a moon, but Makemake appeared to be flying solo. That changed in 2015. Using the advanced optics of the Hubble Space Telescope, a team finally spotted MK2, a tiny charcoal dark moon lost in the glare of the bright dwarf planet. By watching MK2 and tracking its orbital path and speed, astronomers finally had the reference point they needed to calculate Makemake's mass and internal density. The math revealed that Makemake has an exceptionally low surface gravity, much weaker than Pluto's. This mechanical weakness neatly resolves the 2011 occultation mystery. Makemake lacks the gravitational grip to hold on to a gas layer. Any atmosphere it manages to generate quickly leaks out, drifting away into the cold, empty vacuum of space. That might have been the end of the story. But recently, scientists aimed the James Webb Space Telescope at this rock for one final, hypersensitive look. The Webb data revealed solar-excited fluorescence of glowing methane gas, hovering just above the ice. This localized layer exerts a surface pressure of only 10 picobars, 100 billion times thinner than the atmosphere on Earth. Makemake maintains a ghost atmosphere, a transient wisp of gas that constantly escapes into space while being replenished from the ground below. The surface methane is actively sublimating. Localized warm spots are heating the ice, turning it directly into gas and venting it into space. To keep up with that continuous loss, some researchers suspect Makemake features cryovolcanism, ice volcanoes that actively pump fresh methane from the interior onto the surface to sustain the cycle. For decades, we assumed the outer edges of the solar system were static, frozen graveyards. Makemake occupies a unique evolutionary middle ground, sitting exactly on the boundary between an inert rock and a fully atmospheric world like Pluto. By continuously exhaling its ghost atmosphere, Makemake proves that the Kuiper Belt is a realm of active chemistry and ongoing geological cycles. It forces us to rethink how these distant, icy worlds actually operate. Think of the most iconic images of our solar system, and you're likely picturing the massive, sweeping ice fields of Saturn. Planetary rings are beautiful, but they aren't random. They exist exactly where the strict laws of physics allow them to. The Roche limit is a mathematical boundary where a planet's gravity overpowers the forces holding a moon together. Inside this dashed line, gravity shreds icy debris into a continuous ring. But outside, the planet's pole weakens. Debris inevitably clumps together into a solid moon. For over 170 years, this equation has served as an absolute astrophysical law. It told us exactly where rings can and cannot exist anywhere in the universe. To see how that law was broken, we have to look past Neptune, out into the Kuiper Belt. This is a vast, cold expanse of icy debris and dwarf planets, extending billions of miles into deep space. In 2002, astronomers Chad Trujillo and Michael Brown were observing the night sky from the Palomar Observatory. They spotted something moving slowly against the background stars. At the time, it was the largest object found in our solar system since Pluto. They named it Quaoar. It is a distant, dark world, roughly half the size of Pluto, composed of rock, water ice, and traces of methane. In 2023, astronomers watched Quaoar pass directly in front of a distant star, an event known as a stellar occultation. The resulting graph shows starlight dropping as Quaoar blocks it. Notice the narrow dips before and after the main body. These blips prove Quaoar has rings. Plotting the Roche limit reveals the outer ring is 4,000 kilometers away, double the maximum possible distance. According to standard orbital mechanics, the particles in that outer ring shouldn't be a ring at all. They should have combined to form a moon decades ago. To understand why Quaoar's debris hasn't formed a moon, we examine its extreme environment. Orbiting about 43 times further from the Sun than Earth, Quaoar sits in a deep freeze of about 44 Kelvin, or minus 380 degrees Fahrenheit. At temperatures that low, the physical properties of water ice change. The particles in Quaoar's ring don't act like wet snow that easily packs together. They behave more like solid glass. This animation shows what happens when these super-chilled ice particles collide in orbit. They don't stick. They aggressively bounce off each other in highly elastic collisions, repelling one another like billiard balls. Then there is the dwarf planet itself. Quaoar is not a perfect sphere. Instead, it is a triaxial ellipsoid, a shape resembling a slightly squashed and stretched ball. This 3D wireframe models how that irregular shape projects mass. As the stretched dwarf planet completes its 17.7-hour rotation, it generates a lopsided, uneven gravitational field that sweeps outward through space. The extreme cold stops the ice from easily fusing together, while the planet's lopsided gravity keeps the surrounding debris field in a state of constant agitation. But Quaoar's lumpy spin is only half of the gravitational equation. The dwarf planet also hosts a 165-kilometer-wide primary moon named Weywatt, and astronomers have identified a likely second moonlet discovered in 2025. This orbital map shows how these bodies interact through a mechanism called spin-orbit resonance. Quaoar's rotation, the ring particles, and the moons are all moving at mathematically synchronized intervals. A gravitational tug-of-war plays out across the system. Quaoar's mass pushes the ring particles from the inside, while Weywatt and the secondary moon periodically pull on those same particles from the outside. Because the timing is perfectly synchronized, these opposing forces trap the elastic ice.
The particles are constantly nudged back and forth, forced to stay spread out in an irregular, lumpy band of debris, instead of settling down and accreting into a moon. Quaoar isn't breaking the laws of physics, it's using them. The dwarf planet maintains a delicate, highly localized gravitational balancing act that simply overrides the standard mechanics of the Roche limit. If we zoom out from the isolated Quaoar system, we see the broader reality of the Kuiper Belt. For decades, it was easy to assume this outer region was a static graveyard of dead rocks and leftover comet dust. But closer observations reveal a dynamic environment. We are finding worlds with active cryovolcanism, spewing icy slush, scars of ancient collisions, and incredibly delicate gravitational ballets playing out in the dark. It turns out the Roche limit is a reliable guideline for observing massive gas giants in our immediate cosmic neighborhood, but it is not a universal absolute.
As our technology improves and we peer deeper into the outer solar system, tiny, irregular worlds like Quaoar are proving just how complex orbital mechanics can be and forcing us to rewrite the rules of our cosmic backyard. Out past the familiar warmth of the sun, the solar system gets dark and cold. This is a vast cosmic frontier filled with thousands of ancient, icy bodies drifting quietly through the void. To understand why this region matters, we have to look at our standard cosmic map. We have the rocky inner planets near the sun, the massive gas giants further out, and finally the Kuiper Belt, a dense ring of frozen debris orbiting just beyond Neptune. Neptune acts as the gravitational bouncer of this outer edge. Its massive gravity pushes and pulls on these smaller Kuiper Belt objects, scattering them into highly elongated orbits and keeping the entire neighborhood under its influence. But in 2003, astronomers scanning the sky at the Palomar Observatory spotted something that didn't fit the map. They found a faint point of light creeping incredibly slowly across their screens, sitting a staggering 10 billion miles away, about 100 times the distance between the Earth and the Sun. They named it Sedna. Roughly the size of Alaska, it ranks as one of the largest trans-Neptunian objects ever discovered. Finding an object this massive at such a distance showed that our models of planet formation were incomplete. Large worlds were somehow forming or surviving much further into the void than we previously thought possible. What makes Sedna so perplexing is its path. It travels on an extreme, stretched-out oval orbit that takes more than 10,000 years to complete, swinging out to an astonishing 937 astronomical units from the Sun. But the true anomaly is its closest approach. Even at its nearest point, or perihelion, Sedna never comes closer than 76 astronomical units. That leaves a massive, empty physical gap between its path and Neptune's orbit. That specific distance creates a mechanical paradox. Sedna is entirely out of Neptune's gravitational reach, meaning it couldn't have been scattered outward by the giant planet. Yet it sits far too close to the Sun to belong to the Oort cloud, the shell of comets at the very edge of the Sun's gravity. By the known laws of celestial mechanics, Sedna is stranded in a cosmic no-man's land. Nothing is supposed to exist there, leaving a glaring question. How did an Alaska-sized rock get parked in empty space? To understand how Sedna arrived here, researchers looked at the object's specific physical characteristics, starting with its rotation. Early observations suggested a sluggish 20-day rotation, which usually implies the gravitational drag of a moon. But better measurements revealed it actually completes a spin every 10 hours. Sedna is entirely alone. It also has an extreme visual signature. The surface is heavily coated in tholins, a dark organic sludge created when simple ices like methane and nitrogen are baked by cosmic radiation over billions of years. This long-term radiation exposure makes Sedna one of the reddest objects in the solar system. Its surface reflects a deep crimson hue that rivals the color of Mars. More importantly, that deep red color is completely uniform. There are no bright patches of fresh ice or recent impact craters to break up the surface, which we frequently see on objects closer to the Sun where collisions are more common. A pristine, unscarred surface suggests that Sedna wasn't recently knocked into its strange trajectory. It has likely been drifting undisturbed in this void since the earliest days of the solar system. Curious, if the known gas giants like Neptune couldn't reach Sedna 4.6 billion years ago to pull it into this remote orbit, a different, massive gravitational force must have done the job. One possibility lies in the Sun's birth. Stars form in dense, chaotic clusters, and the collective gravitational pull of those ancient stellar neighbors could have dragged Sedna outward before the cluster eventually drifted apart. Or it might have been a close encounter. A rogue star passing near the early solar system could have grazed our outer debris disk, gravitationally ripping Sedna onto its new, elongated path. Some researchers suggest Sedna might not be native to our solar system at all. The Sun's gravity could have stolen the object from a passing alien star system entirely. Then there is the possibility of an unseen giant. A massive, undiscovered planet could be lurking in the outer reaches of our own solar system, actively pulling Sedna and other distant objects into these bizarre orbits. Whichever theory is correct, Sedna is a surviving record of a massive gravitational event from the deep past. Since 2003, we have identified other objects with similar orbits, defining a distinct group of bodies that inhabit this inner Oort cloud. Its discovery forced us to rethink our boundaries, proving that a region previously thought to be empty was actually filled with massive planetary bodies. Locked in a deep freeze at -400 degrees Fahrenheit, and existing in a region so sparse that collisions are nearly impossible, Sedna is a perfectly preserved 4.6 billion-year-old time capsule. By determining exactly which force pulled Sedna into the dark, astronomers hope to map the specific environmental conditions of the space where our sun was born. Sedna remains a physical record of the early solar system, offering a direct link to the violent, chaotic environment of our own origins. This map identifies the Kuiper Belt, a vast ring of icy debris stretching far beyond the orbit of Neptune. Historically, astronomers have viewed this region as a deep frozen graveyard, filled with ancient, stagnant remnants left over from the birth of the planets. Tucked inside this distant zone is Orcus, a dwarf planet candidate about 910 kilometers wide. At first glance, it appears to be a typical resident of the outer solar system, a dormant, unchanging sphere of rock and ice. But when infrared telescopes scanned the surface, the data revealed a glaring anomaly. Orcus is heavily coated in pristine, crystalline water ice, along with distinct chemical traces of ammonia. This composition defies the standard physical laws of the deep freeze. Crystalline ice has a highly organized atomic structure, but in the Kuiper Belt, constant bombardment by cosmic radiation should rapidly blast those neat crystal lattices into a disorganized, amorphous mess. Forming these crystals in the first place requires a significant heat source to melt the water, while the detected ammonia acts as a powerful antifreeze. Neither of these chemicals belongs on a world that's been geologically dead for billions of years. An object this far from the sun should not look this chemically fresh. It stands as a contradiction to the environment around it, a world that somehow managed to completely pave itself in fresh ice, despite the unrelenting cold. To find the source of that heat, we have to look back to the chaotic early days of the solar system. Orcus was likely born from a massive collision between two planetesimals, an impact that shattered both bodies, ejecting a dense cloud of debris into space. Much of that debris eventually coalesced to form Vanth, a moon that is disproportionately massive compared to its primary. At roughly half the diameter of Orcus itself, Vanth is one of the largest satellites relative to its parent body in the known solar system. Tracking Vanth's 9.5-day orbit reveals the system's exact gravitational pull and total mass. This gives Orcus a bulk density of 1.4 to 1.5 grams per cubic centimeter, indicating a differentiated world. Heavier rock sank, forming a central core, while a lighter water-ice mantle floated. The discovery of Vanth proves Orcus isn't a random lump of frozen rubble. It is a highly structured world with a distinct internal anatomy. While Orcus differentiated, the giant planets aggressively migrated outward. Neptune pushed into the primordial disk, scattering thousands of icy objects. Most of those objects were thrown into the deep void, but Neptune caught Orcus in a gravitational tether. The two bodies became locked in a 2 to 3 orbital resonance. For every 3 orbits Neptune completes around the Sun, Orcus completes exactly 2. This mathematical rhythm ensures they remain geologically separated, preventing a collision. This resonance classifies Orcus as a Plutino. It shares Pluto's exact orbital mechanics, but is anti-aligned in space, meaning that when Pluto is closest to the Sun, Orcus is at its farthest point. This gravitational dance saved Orcus from being ejected into interstellar space, anchoring it as a permanent fixture in the Kuiper Belt for billions of years. With a stable orbit and a rocky core, the conditions were set to solve the mystery of the pristine crystalline ice on the surface. Early in its history, decaying radioactive elements inside the rocky core generated immense internal heat. This energy radiated outward, heating the base of the icy mantle from below. This heat melted the inner ice, creating a vast subsurface ocean. Ammonia acted as a vital antifreeze, lowering the freezing point and allowing a slushy layer to persist. Internal pressure forced this mixture through crust fractures, erupting as cryovolcanoes and freezing into smooth crystalline ice. The mysterious surface isn't a paradox, but the frozen remains of massive eruptions that effectively repaved the entire world. This era of activity couldn't last forever. Eventually, the radioactive fuel in the core was depleted, and the internal heating engine began to shut down. While Orcus shares Pluto's precise orbital resonance, it lacks Pluto's scale. Its smaller mass and weaker gravity meant it was unable to hold on to highly volatile gases like methane or nitrogen over solar system timescales. Without these volatiles, Orcus could never develop an atmospheric blanket to insulate the surface or drive the complex weather patterns seen on larger dwarf planets. As the interior cooled, the subsurface oceans froze solid, and the cryovolcanoes went permanently silent. This has left Orcus as a perfect geological time capsule. Because it is geologically and thermally dormant, it remains a pristine, unchanging record of the violent youth of our solar system.
Beyond Neptune lies the scattered disk. It is a freezing, chaotic expanse of the outer solar system, where objects are so incredibly distant they barely reflect any sunlight back toward Earth. In July 2007, astronomers scanning the sky from the Palomar Observatory in California spotted a faint speck slowly crawling across this dark frontier. They carefully tracked its movement to calculate an initial orbit, giving it the temporary astronomical designation 2007 OR10. Calculations based on its faint light and extreme distance indicated a massive body. Finding an object of this scale so far out made it one of the largest unnamed worlds in our solar system, leading researchers to a logical, but flawed, conclusion about its composition. Because of its size and location, astronomers assumed 2007 OR10 was covered in a fresh layer of highly reflective water ice. They envisioned a pristine, frozen sphere, leading to the informal nickname Snow White. Years later, researchers used spectroscopes to analyze the object's reflected light, looking for the specific chemical fingerprints of that white, icy surface. This chart contrasts the expected neutral signature of a white world with the data actually received. Instead of a flat reflection, sensors detected extreme red wavelengths. The object was actually one of the reddest bodies ever found in the solar system. The collapse of the Snow White theory proved that the outer solar system contains a diverse array of complex worlds, triggering a deeper investigation into what this red object was actually made of. A close-up view of this world reveals a battered, heavily textured landscape, saturated in deep crimson. That coloration is the result of tholins, complex organic compounds formed when ultraviolet light bakes simple chemicals, like methane, over billions of years. However, the data reveals a conflicting signature. Alongside the red tholin peaks, a sharp dip at 1.5 micrometers indicates water ice. To explain this, scientists point to ancient cryovolcanism, suggesting liquid water erupted and froze over the red organic crust. This chaotic mixture of ice and organics describes a world with a geologically active past that permanently scarred its surface. In 2016, the Kepler Space Telescope tracked the object's rotation and found another anomaly. While neighboring objects spin every 6 to 12 hours, this world takes 22.4 hours to complete a single day. Maintaining a rotation this sluggish requires a gravitational tether. In this model, we see how a smaller companion body's orbit exerts tidal drag on the host planet, gradually draining its angular momentum and slowing its spin. Using this physics-based hypothesis, astronomers searched archival images from the Hubble Space Telescope to find a companion they had previously overlooked. In 2016, they confirmed a 100-kilometer-wide moon, later named Xiangliu, orbiting the dwarf planet every 25 days. Math and physics successfully predicted the existence of an invisible moon simply by observing the sluggish rotation of the planet it orbits. This overhead map highlights the object's extreme 554-year orbit, stretching from 33 to over 100 astronomical units, tilted at a severe 30.7-degree angle. It's locked in a 3 to 10 resonance with Neptune, completing exactly 3 orbits for every 10 of Neptune's. Because of these traits, the Snow White name was officially replaced. Following a public vote, the International Astronomical Union named the object Gonggong.
In Chinese mythology, Gonggong is a water god responsible for flooding and tilting the earth. The name fits a red, watery world defined by internal eruptions, a severe orbital tilt, and a disruptive history. 225088 Gonggong is a massive, cryovolcanic dwarf planet candidate, rotating slowly as it moves through the deepest reaches of the solar system. Its discovery overturns the assumption that the scattered disk is populated by uniform, static ice rocks. Each faint dot of light here is a complex world, with a unique history, waiting to be decoded by those willing to look closer. When we look at the outer edges of the solar system, we often see a lonely void, an empty space containing a few frozen rocks left over from the dawn of time. That perception hardened in 2006. During the International Astronomical Union assembly in Prague, Pluto was formally reclassified because it lacked the mass to gravitationally clear its orbital neighborhood of other debris. But the geophysical reality of the outer system is far more complex. Astronomers estimate there are hundreds of these worlds, like Sedna, Orcus, and 2017 OF201, that possess the necessary mass to pull themselves into nearly perfect, geologically active spheres. In terms of sheer numbers and available surface area, these dwarf planets represent the primary dominant terrain of the outer solar system. We find the first step of this frontier at Ceres, the closest dwarf planet. While the Moon and near-Earth asteroids are nearby, Ceres contains massive reserves of water ice and nitrogen, the specific volatile resources required for long-term life support that are scarce in the inner system. Dr. Pekka Janhanen's Ceres megasatellite concept lifts surface resources via a space elevator to a disc-shaped settlement in orbit. To prevent physiological damage from low gravity, rotating O'Neill cylinders spin to generate a full 1G of artificial gravity. Reaching beyond this hub requires the direct fusion drive. This conceptual engine burns deuterium and helium-3 to produce a high-temperature plasma, generating the massive thrust needed to deliver heavy payloads to the outer system in just a few years. This infrastructure transforms the asteroid belt into a staging ground. With fuel and supplies secured at Ceres, human missions gain the range to reach the moons of the gas giants and the vast organic reservoirs waiting in the Kuiper Belt. But over billions of years, the stability of these outposts will face a larger threat. The solar system is part of a crowded Milky Way, moving through a field of passing stars that exert constant, if subtle, gravitational pulls. Astronomers view these flybys like darts thrown at a dartboard. While most passes are too distant to matter, simulations show a 5% probability that a passing star will come close enough to fatally perturb Pluto's orbit over the next 5 billion years. A direct hit from a passing star would trigger a chaotic chain reaction. Pluto would be gravitationally scattered by Neptune and passed inward toward Uranus and Saturn, eventually reaching Jupiter, where it would be ejected into the interstellar void. The long-term survival of the outer solar system is entirely dependent on the unpredictable movements of our stellar neighbors. 5 billion years from now, a more certain destruction arrives from our own star. As the sun exhausts its core hydrogen, it will swell into a massive red giant, expanding its atmosphere out toward the orbit of the Earth. This expansion will result in the thermal destruction of Ceres. The intense solar heating will cause the dwarf planet's water-ice mantle and volatile ammonia to rapidly sublimate, boiling away into space and leaving behind a scorched, dehydrated core. The very resources that made Ceres a vital oasis for early colonization also ensure its total eradication as the sun evolves. This phase creates a strange geographic shift. While the inner worlds burn, the habitable zone, the region where liquid water can exist, pushes steadily outward past Neptune, finally settling over the Kuiper Belt. Frozen worlds like Pluto, Eris, and Triton will experience a sudden surge in radiation. Their surface temperatures will rise from deep freeze levels into a range equivalent to Earth's modern tropical regions. These frozen dwarf planets will physically transform. Their ancient ice sheets will melt into deep liquid oceans, shielded by new, dense atmospheres, rich in nitrogen and organic compounds. These former outcasts represent the solar system's final sanctuaries, briefly providing the warmth and chemistry required for biochemical evolution to begin. This habitable era is temporary. Eventually, the Sun will expel its outer layers, leaving behind the small, cooling core of a white dwarf. This mass loss breaks the solar system's balance. As the Sun sheds mass, its gravitational grip weakens, causing the giant planet's orbits to widen. This dissolves the outer anchors. The resonance keeping Pluto from colliding with Neptune breaks, removing the protection keeping their path stable. Systemic stability depended on the Sun's mass. Without it, the outer system collapses into gravitational chaos. This collapse triggers a final scattering event. Pluto and the other dwarf planets suffer violent, close gravitational encounters with the drifting gas giants. These encounters will act as gravitational slingshots. Pluto and its siblings will be hurled completely out of the solar system, their new oceans freezing solid as they enter the interstellar void. The dwarf planets are the dramatic final chapter of our story. Long after the Sun has dimmed, these rogue wanderers will drift through the galaxy, carrying the frozen remnants of our solar system's last habitable oceans.